In this unit, we are going to look at something called permutations. Permutations are a way of counting things, and as you can probably imagine, for probability, the ability to count outcomes accurately is going to be really important. Obviously, if we're dealing with a small number of outcomes, then counting is easy, and we can do it the way we've always been doing it. However, when we're dealing with probability, counting, we often have to count very large numbers of outcomes, and so we need some techniques to be able to do that. So that's what permutations is, one of those techniques. We're not going to look at permutations in this lesson, but that's what this second unit's about. So lesson 2.1 is more about just this idea of organized counting, and in particular a little bit more on tree diagrams. Creating a tree diagram is often useful and sometimes necessary to determine the number of ways that something can occur. To identify a given outcome in a tree diagram, read across a distinct path. We've already seen that. We've done a little bit with tree diagrams already. Excuse me. And we've seen that one outcome would be one distinct path. To determine the number of outcomes in a tree diagram, we count the number of distinct end paths across a tree diagram. So again, once we get to the last stage of a tree diagram, we can then just count up the distinct paths. Let's look at a couple of examples just to illustrate some of the work that we do with tree diagrams, or could do. Abby makes 2 stops on her way to school. She picks up her friend Reagan, then stops to get her breakfast at a coffee shop. There's 3 routes from her house to Reagan's. There's 2 routes from Reagan's house to the coffee shop, and then 1 route from the coffee shop to school. How many possible overall routes are there? So we got Abby starting at her house. Okay, here's Abby's house. Well, let's draw it as a nice little box. Okay, that should have been a box. Try one more time. Strange. Anyway, there's Abby's house, and she wants to go to Reagan's house. Didn't work that time either. How disappointing. So she has 1 route. Maybe 1 route goes like this. Here's another route, direct route. Maybe there's now it turns it into a shape for me. Really? Here's another route, and here's a 3rd route. So those are representing 3 different paths from Abby's house to Reagan's house. And then from Reagan's house to the coffee shop, there we go. Now that's what I was looking for. There's 2 paths, so maybe she goes this way, maybe she goes this way, or they go that way. And then to get to school, then there's 1 path. And so how many paths are there altogether? Well, let's call this R1 for Reagan's house, and R2 and R3 and C1 and C2, so 2 ways to get to the coffee shop, and then this path can just be called S. So we could do a tree diagram. So we could start at Abby's house, and from Abby's house we got 3 branches. We can go to R1, we can go to R2, we can go to R3. All of them represent Reagan's house, but they're all different ways of getting there. Assuming that she went to Reagan's house on the first path, so let's assume she went this way, then she's going to the coffee shop. And again, there's 2 ways to get to the coffee shop, C1, C2, either way you get there. If she went to Reagan's house the second way, there's still 2 ways to get to the coffee shop, right? So 2 paths from there, C1, C2 again, and then the 3rd way of getting to Reagan's house still leads to 2 paths to the coffee shop. And so we can already see that there's 6 different routes they could take. Then to go to school, well, there's only 1 way to get to school. So it's not even really a tree well, it's still a tree diagram, but there's really nothing new going on this level. Once you're at the coffee shop, there's only 1 way to get to school. Well, I see 1, 2, 3, 4, 5, 6 different paths to get from Abby's house to Reagan's house to the coffee shop to school. So tree diagrams can help us see that. However, we could also see that if there were 3 ways to get from Abby's to Reagan's and 2 ways to get from Reagan's to the coffee shop, 3 times 2 is 6, times the 1 way to get to school, that would also tell us our 6 routes. Consider a test with 5 true-false questions that have 2 possible answers, true or false. How many possible answers are there? Use a tree diagram to illustrate. All right, so we've got, let's imagine the test is in front of us, and we've got our first question. We can either choose true or we can choose false. Let's see. Let's draw it like this. So true, false, that was my first choice. That was question 1. Q1. If I chose, whether I chose true or false on the first question, I still have 2 choices. I've got true or false. So if I got true on the first question, it's still true or false on the second question. And if I chose false at first, I still have true or false. And then you can see this is going to keep repeating. So from question 3, I've got true or false. On question 4, I've got true or false, of course. And unfortunately for me, there's yet one more question. Question 5. Oh boy, let's see if I can do this. True, false. Let's draw a bunch of branches to start with. True, false, true, false, true, false. I'll do them in groups of 4. And one more group of 4 should do it. All right. So this brings up one of the first points that we see with tree diagrams. They're great for doing some fairly simple concepts, mapping them out, but they quickly get unwieldy if you were to count up all the different paths we have by counting the ends of the paths. You'd see that there's actually 32 different paths, right? I could have a path that goes true, 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 however many, 5 times. Or, you know, I could have a path that goes true, false, true, true, false, just to randomly choose another one. Or a path that goes false, 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 true. You know, so 32 different unique combinations. So 32 ways to answer this test. Interesting when you think about it, 5 questions turn out to be 32 different ways. And in fact, really, we could come up with the number of paths without even drawing the tree diagram in this case. Because if there's 2 options for each question and there's 5 questions, that means that it's actually, what we have going on is an exponential situation. We've got 2 questions, 2 choices to the exponent 5. Every time we add another question, we're doubling our number of paths. So after question 1, we only had 2 possible outcomes. But after 2 questions, there are actually 4 different paths, right? 1, 2, 3, 4. Those are the 4 different paths. If it had ended there would have been just 4 choices. You can see that if we go to, and one more question though, we double to 8 different paths, and then 16, and then 32. So again, we can use this idea of exponential, an exponential relationship to figure out the number of possible answers there are. Let's take a look at another one. Oh, and by the way, before I move on, just to recall what we talked about in our last lesson, independent versus dependent outcomes, this would be a case of independent outcomes. So every question can be true or false, and it doesn't matter what the question before was. It has no effect. So since each event in this chain of 5 questions doesn't affect the one that comes after it, it's an independent outcome. And that affects, again, dependency or independent will affect the number of outcomes we could have and how those outcomes express themselves. A jar contains a red, a blue, and a yellow ball. Draw a tree diagram to illustrate the outcomes and highlight the ways of selecting yellow, red, blue if replacement of balls occurs. Highlight the ways of selecting yellow, red, blue. Anyway, let's start by drawing the tree diagram. So replacement of balls occurs. That is important again. That's very, very crucial that we know whether or not they're putting the balls back in. So we got this jar, and we're going to pull, it's got 3 balls in it, 1 of each, and we're going to pull out a ball and we're going to put it back in.
Here's a result from search.
Sorry, my phone just decided that I was talking to it. Let me just get rid of that. So the only thing that's not expressed here is that it doesn't say how many balls we're drawing. So I guess the assumption is that we're going to draw 3 balls. Because there are 3 balls. However, hopefully you can see that if we put the balls back in after we draw each time, that we could in fact draw an infinite number of times. We could just keep going forever. So let's assume we're drawing 3 times. That'll go along with part B, where we don't replace the balls, therefore we only could draw 3 times. All right, so if replacement occurs, then on our first draw, we could have red, let's do it in the order given, red, blue, yellow. And then for the whatever I get, if I get red or blue or yellow, I put that ball back in, which by the way makes this situation independent. Again, highly important to be able to recognize independent events. So it doesn't matter if I draw a red, a blue, or yellow on the first one, because I'm putting that ball back in and draw again. I can get red again. I could have got red the first time and red the second time. I could get blue, yellow, and it doesn't matter. I'll get the exact same 3 choices on the second draw. And then on the third draw, again, I'm going to put that ball back in, so I've still got the 3 to choose from. And again, the tree diagram starts to get a little bit messy already. Running out of room here already. Red, blue, yellow, red, blue, no, that says blue. Red, blue, yellow, red, blue, yellow, so there's my tree diagram. Again, kind of awkward, kind of long and a pain in the butt, but we do have it there, and we can see all the different possibilities. So again, I could draw red, red, red. Or randomly, I could go red, yellow, red. Or I could go blue, blue, yellow. Or yellow, yellow, yellow. I could get any combination. And if you count up the number of paths, there's actually 27 different outcomes. Again, an outcome is a whole path that's been taken. And all possibilities in all possible orders are accounted for. Now, if no replacement occurs, that's a big game changer. No replacement means that if I happen to get a red the first time, then the second one I'm going to draw, I only have 2 balls to choose from, and red isn't one of them. So that really is going to cut down on my options. And it's also going to affect what happens afterwards. So if I do draw a red the first time, that means that I can't draw a red the second time, so my second draw will depend on what my first draw was. So it's dependent. So my tree diagram starts out the same. 3 branches, red, blue, yellow. But on my second draw, because it's dependent and I'm not putting the balls back in, if I draw red the first time, then I can't draw red again. I can only draw blue or yellow because that's all that's left. If I draw blue the first time, I can't draw it again. I can only draw red, or I could draw yellow. And if I draw yellow the first time, I could then draw red, or I could draw blue. So we've got less options now in this case because of the dependency. And if I drew a red followed by a blue, all that's left is yellow. I have to draw yellow on my last draw. If I did red then yellow, I'd have to draw blue on the last draw. And so depending on what went before, it's going to change each time. Blue, red, yellow, blue, yellow, red, blue, yellow, blue, red. Those are the only options. So there's only 6 paths in this case. I'm supposed to say outcomes. So there are 6 outcomes compared to the 27. And so they're very limited because of the differences. But in each case, we can see certain things, usefulness and limitations of tree diagrams. They're really good for helping us visualize things, but they also they get awkward quickly if we have too much information we're trying to organize.